Hello everyone, this is video 6.1. We're going to be looking at integer division. So division of whole numbers, positive and negative. It'll be, mostly we'll look at positive because we already know the rule that applies since we've done multiplication, but we'll come to that shortly. But here we go. So we need to define some terms as usual at the start of a chapter. It's a good place to start. So we'll define these three terms here. So we have the quotient. The quotient is the solution to our division problem in the same way that the product is the name of our multiplication answer, or the sum for addition, or the difference for subtraction. So it's a pretty key term to know what to call our answer rather than just calling it the answer. The dividend is the number which is to be divided. And it's kind of not a great definition. So if we look at an example, we say m divided by n equals p. So then this would be my dividend, because that's the number that's going to be divided. And then it gets divided by n, which is my divisor. So my divisor right there, and then that gives me a quotient. So that gives me a quotient there, which we could call P. So these are the three parts to our division problem. So we can connect this back to multiplication the same way we did with subtraction and addition, and create what these fact family problems, what some people like to call these fact family problems. So as an example, we could start off with the multiplication problem. 3 times 6 equals 18. And there should be 4 total problems, so 3 more that we can sort of make that are connected with this, that are part of this family. So the other one would be 6 times 3 equals 18. So these are my two multiplication problems. These are my two multiplication problems, and these show the commutativity of multiplication, that I can do the 3 times 6 or the 6 times 3. And we can connect this back to our rectangle that we've looked at so many times already this semester. And so we have our 3 by 6 rectangle and our 6 by 3 rectangle. However we want to understand that 3 by 6, if we want to do the 3 being the height and the 6 being the width, or vice versa, whatever. So we've got our 3 by 6 rectangle from this. Now, the division extension of this, we could do 18 divided by 3 equals 6. So we have 18 squares here, or probably technically rectangles. So we've got 18 units inside this rectangle, and if we put them into 6, then we get 3. Now, the commutativity doesn't apply here because we can't also do 3 divided by 18 equals 6. So you're going to see students who want to apply the multiplication pattern to division, and that simply doesn't work. So we have 18 divided by 6 equals 3. And so this is a good launching point for talking about further, what am I doing? Dividend. Division. There you go. There you go. So this gives, like I said, a launching point for talking about like how we understand what division means. We could do this as an extension of division. We can do this as an introduction to division. Either way, either way works as long as you're sort of mindful about where it fits and what you could do. You could also introduce this, get into a more rigorous definition of what division means, and then come back and clarify this model more. It's up to you, but these fact family problems work to sort of show this relationship between multiplication and division. Okay, so there's two models of division that we're going to be talking about. And the first one is what we call the measurement model of division. And so in this model, the group size is known, but the number of groups is unknown. So we'll look at a couple of examples of this one and of the other model, which is on the next slide. But let's take as an example, sort of a word problem for this. Let's say that we have 18 candies. And so the group size is known. So we're going to say that each student gets 6 candies. And so what we want to know is how many students get candies. So we could think about this as repeated subtraction in the same way that multiplication is repeated addition. And in multiplication, we start with 0 and we build up to the product. Now, since division is the inverse operation, it's going to move in the opposite direction. We're going to start with the product, and we're going to subtract down until we get down to 0. Now, that product, in this case, we're going to call the dividend because we're talking about this from a division aspect. So we're doing 18 divided by 6. So it's just like the problem for the previous slide. So we've got 18 minus 6 is 12. 12 minus 6 is 6. And then finally 6 minus 6, that minus sign is not very convincing. 6 minus 6 equals 0. And so we can see 1, 2, 3. So now we know that there are 3 groups. And so that's my quotient is my 3. We knew the size of each group. Each group was 6 candies. So we just want to know how many groups there were of 6 candies, and we could count that off 1, 2, 3, and find that there's 3 groups. So this is the measurement model. And I mean, if you think about what this sort of looks like, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So if you think about what this looks like, I mean, we are literally measuring off. So there's 6. There's 6. There's 6. We're measuring these things off. So I know that these two models can be a little confusing because they're very similar. But I feel like the name is a pretty accurate description of what's going on. In the measurement model, we are measuring these things off. We could think of this as being maybe like 18 ounces of a drink, and we're measuring out 6 ounces at a time. So how many times can we measure out 6 ounces until it's empty? We're removing these groups like we're measuring things off. And so that is our first model, the measurement model. Now the second model is called the partitive model. And this is where the sort of the confusion can sometimes lie, because it's the same idea, but it's switched. So now we have the number of groups is known, but the size of the group is unknown. So let's take 18 divided by 6 equals 3 again. And so now let's say we have 18 candies. And then we have 6 students. Each get an equal amount of candy. So now the question is not how many students, it's the size of the group that's unknown. And so we want to know how many candies does each student get. So now the partitive model is a little bit different because we're not going to measure off 6 candies, 6 candies, 6 candies because that's the measurement model. The way that we see this drawn out a lot of times is we're going to make a column for our 6 students. And so we've got our 18 candies here. And so we're going to subtract off, everyone's going to get 1. So 1, 2, 3, 4, 5, 6. So we subtract the 6 and we get 12. So we know there's still 12 candies left. So everyone gets another candy. 1, 2, 3, 4, 5, 6. All right, there's still 6 candies left. So everyone gets another candy. 3, 4, 5, 6. Ta-da! Everyone got a candy. Excuse me. So again, we have this repeated subtraction, and this subtraction happened 1 time, 2 times, 3 times. And so we can see that 8 divided by 6 equals 3. I want you to really take some time to understand how these two problems, how the models are different. Um, One of the things I like about the partitive model, and the reason it's called the partitive model, is because we're making a partition. So if you know what a partition is, if you've ever done any sort of like construction-y home redesign or watched anything on HGTV or anything like that, where you're putting in a wall and you're creating a partition in a room. Like you take one room and make it into two rooms essentially. And so what we've done, we've taken our 18 and we've put in these partitions here to break that 18 into 6 equal parts. And this equal amount is pretty key to the problem. So we take these 18, we break it into 6 equal parts, but now how many is in each part? How many candies are in each partition? So if you remember partition, then that'll help you remember what the partitive model is, because that's what it's doing. It's partitioning 18. I like this model because at the end, when you do this, you get this 3 by 6 rectangle that we've talked about in terms of the multiplication models before. And you can still do that with the measurement model. And you can think about this, you can still use that in measurement because in a way we've subtracted off these 6. We can still reapply this, I guess what I'm trying to say, to the measurement model. Uh, but they operate differently, and the word problems are different, and the way we think about how these are being done is different. So make sure you understand the distinction between these two models. When we get into fraction division, these two models are going to be crucial. In fact, they're so crucial that each one of these two models gets its own video, gets its own section in the book for each of the two models. So for integer, uh, for integer division, the two models are awfully similar. For fraction division, they're very dissimilar. So we'll have a look at that a little bit later on. So we've already seen what this already looks like as an array a little bit in the previous slide, but just to take a moment to look at this. So if we wanted to keep looking at our 18 divided by 6 equals 3, um, we can draw a rectangle, and then we'll cut across this way, and then here's my 6 and my 3. And really, this gives us our whole fact family sort of representation here, because we've got 3 by 6 is 18, we've got 6 by 3 is 18, and then we've got 18 divided by 6. If we think about it this way, so we could think of this as being 6 groups of 3, and so if we do 6 groups of 3, then we know how many groups we have, and we want to know how many is in each group. And so this would be partitive because we know how many groups we have. But if I look at it maybe this way, so this way to me, I think of as being more partitive. If I look at it this way as groups of 6, then that's measurement. Now, you could certainly argue different perspectives on sort of how we see this rectangle and how we interpret, how we break up this rectangle. This is not the only way to interpret this rectangle. It's the way that I interpret it. But this 6 groups being partitive and groups of 6 being measurement, there's not a lot of interpretation of that. I mean, that's really what this is. So the way we talk about this rectangle, and it's really the difference of 6 groups versus groups of 6. That sounds really, really similar. It's really easy to get that confused. So rather than just memorizing the words, I mean, having an idea what the words are telling us and representing is really crucial to understanding division. We should talk about division by 0 because it comes up. It's a question that some students get really curious by, especially when they've sort of heard that this can't be done or that this is impossible, or even, you get some students who, I've heard this is infinite, they like this idea of infinite. Um, and I've heard teachers address this and just say, well, it's just the way it is, or is this is by definition, which is kind of an awful way to put it. But if you have a way of talking about division, then this makes sense. There's a way to talk about this in a way that makes sense. So let's take our 18 divided by 6 again. And we've already talked about the two different models of doing this, right? And so we have our measurement model where we're going to subtract 6, subtract 6 until we get to 0. And so my quotient, what was the 3, was the number of these groups. My divisor is how much I'm subtracting, right? And so we could use the measurement model to show, well, if I wanted to do 18 divided by 0, so my divisor, again, is going to be what I'm subtracting. Oops, what happened there? So 18 subtracted by 18 minus 0 is 18, minus 0, minus 0, and you get the point. And so over here, we're going to keep going until we get down to 0. This 18 is going to be reduced by 6 until it gets to 0, or as we'll see later on, until we get to where we can't take another full group, and we get to dividing by things where they don't divide evenly, and we get to remainders and fractions. There's another stopping point there. But when we get to this point, but subtracting by 0 is never going to reduce this 18. It's never going to reduce. And so this one, there's no answer to it. This is undefined. So there's no way really to talk about what this does. I would say that we can't even really talk about this as being infinite, because we're not even moving toward that goal. So I mean, I understand the idea that this process is going infinitely, but it's not approaching what we sort of established as this endpoint here. So you know, if students want to talk about this idea, having these models gives us a way to sort of talk about why this doesn't work, why this is an undefined operation. So when we come to integer division, talking about positives and negatives, the same rules apply for multiplication as to division. But in the same way, we don't want to just say a positive divided by a negative equals a negative and not offer some sort of rationale or support for that idea. The same model that we use for multiplication can also be applied to division. So if we remember the pattern that we talked about for multiplication, that's terrible looking. Let me fix that. Okay, so for multiplication, 3 times 2 equals 6. Then we did 3 times 1 equals 3. We did 3 times 0 equals 0. We saw that this factor was decreasing by 1, and my product was decreasing by 3. So the next number in this pattern would be 3 times negative 1 equals negative 3. 3 times negative 2 equals negative 6. And so we can see, again, this factor decreasing by 1, this product decreasing by 3, and we get a positive times a negative equals a negative. Now, if we extend this to division, so we can take 6 divided by 3 equals 2. Now, remember, we're moving this product over here to be the dividend. So now this is going to be 3 divided by 3 equals 1. And then 0 divided by 3 equals 0. And now this can be a little confusing for students because a lot of times they'll say, I thought you said you couldn't divide by 0. We're not dividing by 0, we're dividing by 3. So your dividend can be 0. I'm starting off with 0 things, and I'm removing 3 things at a time. Then I don't have to do it any times at all to be at 0. So 0 divided by 3 is going to be 0. And so now we can see the same pattern is applying here. This is my decreasing by 3, and this is my decreasing by 1. So now this becomes negative 3 divided by 3 equals negative 1. Again, it's not the most rigorous proof in the world, and there's more rigorous ways of proving this. I mean, we can certainly get into negative a divided by a is negative 1 times a over a, all that sort of stuff. I don't know that's really compelling for an awful lot of K 6 students necessarily. So you've got this sort of more airtight method that students are probably not going to engage an awful lot with, and then you have this more of sort of not as rigorous approach that's probably going to be more convincing. I think you want to go with the way that's more convincing. And if the students want or need more rigor later, you can certainly bring that into it if they need it. But I think for right now, seeing this pattern, that's compelling enough. I think that works for our purposes. So our checkpoint problem, 24 divided by 4. I want you to think about how you would explain this using both the measurement model and the partitive model. Um, be able to use both models pretty fluently, and then also think about how you would write a word problem using both of these models. Um, so make sure you understand the distinction between the two, because like I said, they're very different models. They're very different interpretations of division, and when we get to fraction division, understanding the difference between these two models is going to be crucial. So if you have any questions about these two models or anything else from this section, please by all means let me know. All right, thanks.